Okay, this video is going to be examples that use strategies from lesson 5, which was focusing primarily on AND cases, things that are just and then the idea of independent events. Okay, so the first problem here says a jar holds 10 white, 6 red, and 4 blue marbles. If 2 marbles are chosen with replacement, what's the probability that they will both be red? So pause this, give it a try, and then unpause. Okay, so from here, I think the main thing is we're talking about with replacement, which means we're going to draw a marble, record its color, put that marble back, replace it, and then randomize the marbles and draw a second one out. So what you can say is for the first draw, right, we would have 10 white, 6 red, and 4 blue marbles, which is a total of 20 marbles, right? And then when we do the second draw, right, we're going to have 10 white and 6 red and 4 blue marbles again because we're replacing it. So each time we have the same probability. Right, so the probability, I could write it this way, that the first one is red and the second one is red, right? That really should be the probability that the first one is red times the probability that the second one is red given that the first one was red, okay? But because these are with replacement, you could also say that that makes these draws completely independent, right? The probability is not going to change for the second draw because by replacing the ball, they're the same. So because of that, we get to simplify this probability formula in this case. We could say that this is equal to the probability of the first one being red, and then this one's just going to be the probability that the second one is red, and we don't have to account for the first one being red because it doesn't change, right? Because we've placed the ball back. And each of those probabilities would be the same. It would be 6 of the balls out of the 20 are red the first time, and also 6 out of 20 are red the second time, and we multiply for and, so that would be 36 out of 400, or a probability of 0.09. Okay, so that's how we would do that if we had replacement. In the second one, we're going to have the same jar, 10 white, 6 red, 4 blue marbles. If 2 balls are chosen without replacement, what would the probability be that they would both be red? So pause this one and give this one a try. Okay, so if we did this, the first time we draw the marbles, right, we would have 10 white, 6 red, and 4 blue marbles, right? But the second time that I draw, I definitely am drawing one of the red ones out, right? So this one is going to get used up. Right, so we used to have 20 marbles. We drew one out. The second time, we're going to have the 10 white marbles still, but now we're only going to have 5 red marbles left, 4 blues, and that means there's only 19 left. So we have a different situation. These probabilities of each draw are no longer independent of each other because the probability of getting a red the second time has been affected by the probability at the beginning. So that means we're going to have to use the full AND formula. The probability of the first one being red and the second one being red is equal to the probability of the first one being red times the probability of the second one being red, given that we account for the fact that the first one was red. So the probability that the first one's red is out of the 20 marbles, 6 of those were red. And the second probability is out of the 19 marbles remaining, only 5 of those were red. So it would be 5 out of 19, and that means we end up with 30 divided by 380, or 0.0789. So this probability is a little lower than the first problem because there were less red marbles to draw in the second case. So the first one was independent events, and the second one, these are not independent events. Okay, the next problem here says, a fair 10-sided die is tossed 3 times. What's the probability that we get a 7 all 3 times? So give this a pause and then try. All right, so this is the way you should do the problem, or at least one way to do the problem. Yeah, for one roll, for a single roll, what we've got essentially is a 10-sided die. So we could get a 1, a 2, a 3, a 4, a 5, a 6, a 7, an 8, a 9, or a 10. Right? And we want specifically the probability we get a 7. So each of those are equally likely to occur. So I'm going to use the equally likely probability idea that we're just going to define a sample space, right? And that'll determine the count for the denominator. And then for the numerator, we'll define an event space, which is the ones that meet the event criteria to be a 7. So one of those numbers, right? So the probability in any one toss, of getting a 7 is out of the 10 numbers, one of those numbers is a 7, so that would be 1/10, right? So if we're tossing the dice 3 times, then the probability of getting a 7 and a 7 the second time and a 7 the third time, right, really should be written this way. It's the probability of getting a 7 times the probability of getting a 7 given that the previous one was a 7 times the probability of getting a 7 given that the previous 2 of them were 7s. Maybe that'd be one way to write it. Right? The other 2 are conditional probabilities, but because tossing a die is every time the dice rolls, it doesn't remember what it did before. These are all independent events, right? Every dice toss is independent. So really, all of these are just the probability of getting a 7, the probability of getting a 7 in a single toss, which we just found out is 1/10. 1/10, 1/10. So if I multiply across the top, it's 1, and across the bottom, it's 1/1000th, or 0.001. So very unlikely that we would get that because 7 is just one of 10 possibilities, and we have to get it all 3 times. Okay, this one says, a sample of 100 people at a mall were asked to try 2 different soft drinks and state their preference. The results are shown in the table. Some people prefer drink A, some people prefer drink B, and we kept the numbers separate for the males and females. What's the probability that a person selected at random from this group will prefer drink A? What's the probability that they're female? What's the probability that a person that's selected at random is male and prefers drink B? What's the probability that a male from the group will prefer drink A? What's the probability that a person who likes drink B is a male? And then are the events female and drink B, preferring drink B, independent? Explain. Okay, so pause the video and give this one a try. Okay, so this has to do with finding different areas of the table, and mainly it has to do with recognizing which things are simple probabilities and which ones are probabilities that are compound events. So the first one, I could state it this way, it's just finding the probability that somebody prefers drink A. Okay, so that's a simple probability, which means we're talking about the entire table. So if I were to say add across here, I've got 22 and 38, that turns out to be 60 males, 40 females were added up, were surveyed, and if I add the columns, there were 44 people that preferred drink A, and there were 56 people that preferred drink B. So it would be out of all 100 people that were surveyed, how many people liked drink A? So that would be the drink A column total here, which would be 44. So that one would be 0.44, a simple probability. Okay. Okay, for part B, this one says what's the probability that the person will be a female? So I could write that this way, the probability that they're a female. And so again, that's a simple probability. That means out of all 100, I would take the total number of females, which is 40, and so that would turn out to be 0.40. So those 2 are simple probabilities, definitely out of 100. Okay, let's consider the next one, part C. This one says, what's the probability that a random person selected is male and prefers drink B, right? So, I'm sorry, yeah, right. Okay, male and prefers drink B. So the way I could write that is that they have to be male and they have to like drinking B, okay? So there's no line there. That's not a conditional probability. We're still talking about out of all 100 people, right? We would have to be they have to be male and B. So they would have to be in the male row, and they would have to be in the B column. And that's why we use the intersection for and. It's the intersection of those 2 things. So 38 out of 100. In fact, let me back that out for a second. Right? Okay, so it would be 38 out of 100, right? Or 0.38, right? So you can think of it as considering all the people in the table, and then what's the specific case of and there. Right? Or if you prefer, you could use the and formulas, right? Another way to solve that same problem would be to say the probability of being male and liking drink B is equal to the probability of being male times the probability that you like drink B given that you're a male, right? That's the and formula. And it comes from the idea of considering these events to be separate events. Like you could say, okay, I could have male or female, and then I could like drink A or B, right? I'll do B up here. I could like B, or I could like drink A, B, or A, right? So if I were to label that, this would be the probability of male. This would be the probability of B given that male happened, and this would be the probability that B and male happen, or male and B happen, right? Okay, so that means that the probability of B and male, or male and B, same thing, is equal to the probability of male times the probability of B given male, right? That's how I kind of remember that formula. So I use a part of a tree to recreate it, but basically it's this formula right here. It's the AND formula. The second one, if you want to multiply probabilities, and remember that AND, because it has an AND in there, is multiply, well then you would do it this way. You would say the probability of being a male is a simple probability, so out of 100, how many are males? That's 60 out of 100. And then this would be a conditional probability, so the bottom of the fraction is determined by the male part. So only out of the males, which are 60, how many of those like drink B? That's the 38. And it turns out those 60s cancel, and you still end up with 38 out of 100, or 0.38. So both of those are perfectly good ways to solve that problem, either with the AND formula, or you can just go right to that place in the table out of the entire amount. Okay, let's look at D. So D says, what's the probability that a male from this group will prefer drink B? Okay, so you have to be careful in the wording here. It's the a male from the group is kind of a parenthetical comment. We're really finding the probability that somebody will prefer drink B. The probability that somebody prefers drink B, given that the condition is that they're male, right? So this is really a conditional probability. What's the probability that they drink B, given the condition that I could put in a parenthesis of that they're male? So that means that I'm going to use only the male part of the table to be the denominator. So out of the 60 males, the people that prefer drink B, there's 38 of the males, so I'm restricting myself to the first row only, and out of that 38 prefer that. So it'd be 38, but this time out of the 60, and that turns out to be 0.6333. So that would be that probability, a conditional probability. And the one below it there, E, is what's the probability that a person who likes to drink B is a male? So we're finding the probability that they're a male, given that they're a person who likes to drink B. So this time, the bottom of the fraction is determined by drinking B. So that's going to be out of the 56 people that like to drink B, how many of them are males? Which is that same 38. But this time it's 38 out of 56. And so that would be 0.6786. All right, slightly different probabilities there, and it definitely matters which condition we're talking about. And then the last one was, are the events being female and preferring drink B independent? Or you could say, are the variables gender and soft drink preference independent? Right? So the best way to test that is to pick one of the events, like say B, and find the probability of it. If the probability of B is the same, regardless of whether or not you're a female or not, then that means that it's independent of being a female. So you could check the probability of B. Is it equal to the probability of B given female? Is it equal to the probability of given B given that, or of B given that we're not a female, that we're a male? Right? If any two of those are the same, then that means that that it is independent. So I'm just going to pick this one. And I could say, let's find the probability of B. That's a simple probability. So out of all 100, the probability of liking B is 56, right? So this is 56.56, right? And then if I wanted to find the probability of B given female, I would say out of only the females, so that's 40, how many of those like B? That's 18. And 18 out of 40 turns out to be 0.45. Right? Those two things are not equal, so that's evidence that these are not independent of each other. Right? We would say not independent. Right? And that's because the probability of B happening changes whether you're a female or just for everyone in the group. And I just chose randomly to analyze B. I could have decided to analyze female. Right? What's the probability of being a female? Is that the same as being a female given that we're talking about drink B? So the probability of being a female, simple probability, no line there, so it's out of all 100 students. There's 40, so a 0.40 chance of being a female, right? But if you're restricting yourself to the condition of only people that drink B, out of the 56 people that like to drink B, 18 of those are female, right? So that turns out to be 0.3214. And those two things are not equal, and so therefore not independent. So you don't have to do it both ways. You can just pick whichever one. Now, the book often will add something called the test for independence. So if you look at the AND formula, Right? The and formula says, say, the probability of B and female is the probability of B times the probability of female given that B happened, right? The general and formula, this has to be a conditional probability, right? But if it is true that they're independent, if it is independent, then the probability of female given B would just be the same as the probability of female, period. And so you get to simplify the and formula to this. The probability of B and female equals probability of B times just probability of female. This second term doesn't have to be conditional anymore. And so some books call that the test for independence, right? That you can check to see if the simplified version of the and formula works. I don't like doing the problem that way, so this is the only problem I'm going to do that way, but I will show you how it works. I really think these ways over here are better because they get to the heart of what independence means. But if you want to do it this way, right, the probability of B and female would be out of all 100 students, right, being B and female is 18, that one place on the table. Is that equal to the probability of ranking B, which is 56 out of 100, times the probability of being a female, which is 40 out of 100, right? Now, when you multiply those two things together, so this side becomes 0.18, and this other side over here becomes 0.224. So again, those things are not equal, and you would conclude they're not independent. I think that's less intuitive, though, and it doesn't really get to the heart of the idea. So I would prefer that you do the blue or the red way if you were in my class. Okay, let's look. We've got 3 more problems here, I think. Yep, we'll continue on here. A student has an 80% chance of passing their English final and an 85% chance of passing their math final. What's the probability that they will fail both their English and math finals? So pause and give this a try. Okay, so maybe we could start by saying this is an and case, right? So it would be the probability that they fail English and they fail math. That's going to be the probability that they fail English times the probability that they fail math, given that they failed English. Okay. Now at this point, I might ask the question, are these independent or not? In other words, would it be true that failing English has nothing to do with failing math? That may or may not be true. I think for the purposes of this problem, we're going to assume that the tests are independent. But there could be a connection, right? Like what if you were ill? If you were ill and that meant that you failed the math test, you might also fail the English test for the same reason. If that was true, something weird going on like you were ill, then it wouldn't be independent. But let's make the assumption that these are independent. The English and the math finals are independent. I think it's reasonable to make that assumption. If that's true, then this would be the probability of failing English times the probability of failing math, and I don't have to indicate that it depends on whether I failed English. It's just going to be the probability of failing math, period. So what are those probabilities? Well, the probability of failing English, that's going to be 1 minus the probability of the opposite, which is passing English, right? So they told me that the probability of passing English is 80%, so the probability of failing English is 20%. And for math, the probability of failing math would be 1 minus the probability of the opposite, which is passing math. And they told me that the probability of passing math is 85%, so there's a 15% chance of failing math. So then this would be the probability of failing English, which is 20%, times the probability of failing math, which is 0.15. And so this would be 0.03. So there's only a 3% chance, if these probabilities are independent, that you would fail both tests, that the student would fail both tests. Okay, let's look at another problem. It says 6 letters with repetition allowed are selected from the alphabet. What's the probability that none of the letters are repeated? So pause the video, give this one a try, and then unpause. Okay, there's kind of 2 ways to do this problem. It sort of depends on if we're going to focus on the entire 6-letter word as a single event, or if we're going to focus on the selection of each letter as a separate event, and then we have multiple events. So let's do the single event way first. Right, the single event means we're talking about the entire word. We're focusing on the word, right? So if I pick 6-letter words, right, all of them are equally likely to be selected. And repetition is allowed, so we're allowed to have words with the same letters in them in the different spots. So I could use the sample space would be the number of 6-letter words period. And maybe I could use the multiplication principle. There's 1, 2, 3, 4, 5, 6 letters to choose. Repetition is allowed, so all 26 letters in the alphabet are available for the choices. And then I could multiply those all together to get the total number of 6-letter words. There's 308,915,776 6-letter words if you allow repetition. Okay, and then the event space would be specifically that we're looking for the probability that none of the letters are repeated. So that would be just the number of six-letter words with no repeats. With no repeats at all. Okay, so let's use that same counting technique. We have to pick 1, 2, 3, 4, 5, 6 letters. We could pick any of the 26 letters for the first spot, but then we've used up a letter. We have to pick from the 25 remaining letters for the next one. We've used up 2, so there's 24 letters left to choose, and then 23, 22, and 21. We would multiply that, which turns out to be 165,765,600 different unique words. And so the probability of having no repeats would be the 165,765,600 number on the top divided by the 308,915,776 number on the bottom, which turns out to be 0.5366. So if you randomly pick 6-letter words, a little over half of them would have no repeats. So that's if we solve the problem by focusing on the word as a total. That makes it a single event. What if I wanted to focus on the letters? That means we have multiple events. Okay, so I'm going to try to do this with probabilities, right? The probability that they're all unique, that would be the probability that we have a letter, right, times the probability that the next letter, the second letter, is different from the first, times the probability that the next letter is different from the other two, and so on until we've populated all the words, all the letters in the word, right? So the way you could think of this is, this is the probability of picking a letter. Well, that means that probability is 1, right? If I pick a letter, I'm 100% certain to get a letter, right? But the second probability would be, I have to pick a letter that's different from the first one. So out of the 26 letters in the alphabet, I'd have to pick from only the 25 that are not the one I picked first. And then for the third letter, right, out of the 26 letters in the alphabet, I'd have to pick only of the 24 letters, not use the 2 that were used at the beginning, right? And then the fourth letter would be 23 out of the 26 letters, and then 22 out of the 26 letters, 1, 2, 3, 4, 5. The sixth one would have a 21 out of 26 chance of being not the same as any of the previous ones. Now, if you write this one right here as 26 out of 26, then you can see that it's exactly the same thing we calculated. The top of the fraction is going to be 26 times 25 all the way down to 21, and the bottom of the fraction is a bunch of 26s. So this turns out to be the same exact 0.5366 number. So you could either analyze it by looking at the letters and multiplying with and multiple events, or you can consider the entire word as the event and then analyze that as an equally likely cases scenario. Okay, let's look one more problem. If 2 cards are drawn from a standard deck of 52 cards without replacement, what is the probability that the first card is black and the second card is 7 if we know the first card was not a 7? Okay, pause that and then give that a try. Okay, I think in this kind of scenario, I'd like to kind of get a picture, right? We're starting from 52 cards, right? There's we're drawing 2 cards. Okay, so the first card that I draw, I have all 52 cards in the deck, right? And then it said, we know that the first card was not a 7, right? Okay, so of the 52 cards, 4 of those are 7s because we have hearts, clubs, diamonds, spades, right? So there's 4 7s in the deck. So we're going to draw out a card, right? It's not a 7, right? So that means, well, that's the second draw. We're going to have 51 cards, right? But all 4 7s are still in the deck, are in the deck. Okay, maybe I'm just using that to kind of wrap my head around what's going on here. All right, so what are we doing here? We're finding the probability that the first card is black, and the second card is a 7. So I might have to change what I wrote over there. The first card is black, and the second card is a 7. So and the second card is a 7. Okay. All right. So let me just go. Actually, I think I need to redo this. So we start with the 52 cards, right? So this is definitely going to be the probability that the first card is black. First card is black. Times the probability that the second card is a 7 given that the first card is black, right? We're also told that the first card was not a 7. So really this should be written, the first card is black but not a 7. And this is the probability that the second card is a 7 given that the first card is black but not a 7. Okay, I'll write it like that. This is not really official notation, but it'll help us figure it out. So what's the probability that the first card is black but not a 7? Okay, so of the 52 cards, right, half of them, 26 of them are black, and another 26 are red, right? And so the probability that I would get a black card, but not a 7, because actually, let's see, so 2 of these are 7s, so right, we have 2 7s that are red, and then we have, let's see, 24 other red cards. And then same thing over here, I have 2 black 7s, clubs and spades, along with 24 other black cards, right? So what can I really pick? It has to be from the black area, but not the 7s. So it's just going to be these 24 cards here, right? Would you agree? All right, so this is going to be 24 out of the 52 cards. That's the probability that the first one is black, but not a 7. All right. The second one, this is going to be, we're drawing a card, right? There are 51 cards left in the deck, but we have to this time draw a 7, okay? So all 1, 2, 3, 4 7s are still in the deck because the first one wasn't a 7. So that would be 4 out of the remaining 51 cards. And then we could do that in a calculator. Let's see, that would be 24 divided by 52 times 4 divided by 51. So that should be 0.0362. 0.0362. All right, so that's how I would solve that problem. Okay, that's it for this. It's hard to make examples that only use and or very, very rarely use or. We usually more with and or. So there's a lot more examples in the lesson that talks about and or together.